Hey again, everybody. If you watched the last video and you're going right into this one, this is just a continuation. The only difference is I'm going to switch which particular functions we're going to use, which particular series. So in this corner, we're going to use our good old friend, the harmonic series. And by the way, if you need any explanation or further explanation about the harmonic series, I did have a video that I put up on just the harmonic series, so that may help. So in that corner, we've got the harmonic series. In this corner, we've got 1 over x. Not nearly as exciting. Oops. Just 1 to infinity, sorry. So we have this, not negative 1, just 1. Okay, so we have our series 1 over n versus 1 over x, and we're going to do the same exact strategy we did before. We're going to look at a good picture. And here's our picture for 1 over x. Basically looks the same. And we're going to go ahead and do rectangles, but this time I am going to do left-hand rectangles instead of right-hand, because this time I do want to actually be above the curve, and I'll explain why in a minute. So 1, 2, 3, 4. So left hand would be like this. Let's get at least one more in there. Okay, and if we look at the areas of those rectangles, I have base times height, so base is 1, height is 1 over 1, right? F of x equals 1 over x. My area of this one will be 1 times 1 over 2, 1 over 2, 1 over 3, 1 over 4, etc. So again, it resembles my series, 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 2, etc., etc. And the same argument can be made. If I were to find the area of all of these rectangles and put them all together, it would look like this series. Okay? I don't need to do any balancing act for this one, by the way, simply because I don't have that rectangle that's to the left of my starting value for my integral. Right? The last time I had the rectangle over here, and it wasn't accounted for in this integral, so I had to add it in. But this is a perfect matchup of area of the rectangles compared to area under the curve. Okay, and clearly you can see that all of these rectangles are above the curve. Even if it gets close and close, it's still going to be above. So I don't think it'd be too much of a stretch for me to say that the series, the sum of this series, is going to be greater than the value of this integral, because all of these rectangles are above my curve. So my curve's area is in purple here. My rectangle's area clearly has some extra space. This would have been an overestimate in the olden days. Olden days being like 3 months ago. Okay, so this series is bigger than this integral. What does that mean? Well, suppose this integral converges, right? Like I sort of mentioned at the end of the last video. If this integral converged, and saying that my series is bigger than that, that doesn't really give us any information. If this integral converges to, say, 10 or something, this could be 11, it could be 15, it could be 94, it could be 8 billion. That would all be fine. But what if it goes to infinity? How do we know? We don't. So we'd have to say that this is an inconclusive test. We wouldn't be able to use this test to find anything out of any value. Okay? But if this integral diverges, and we show that this series is bigger than a divergent series, well then, a divergent integral, then this series must also diverge because it's bigger than something that doesn't have a boundary. Okay, so if this is going off to infinity, if this integral is going off to infinity, well then the series must be going off to more than infinity. But that's still just infinity. So we would just say that this series diverges, and that's what we're going to show this time. So this integral, I'm going to go ahead and do the same improper technique, which sounds terrible, but it's the proper improper technique, if you will. And I'll do that over here. So that's going to be a limit as t goes to infinity, 1 to t. And this time I cannot do my reverse power rule. This time 1 over x, I have to use my sort of special case antiderivative. And the antiderivative of 1 over x, of course, is the natural log of the absolute value of x. And we're going to evaluate that between 1 and t. Okay, just so happens all my values are going to be positive anyway, so the absolute value is really not necessary. I'm just showing it because that's technically what the antiderivative is. So this limit as t goes to infinity is going to be for ln t minus ln 1. Okay, ln 1 of course goes to 0, so that's really not any help. And then as t goes to infinity, ln t, well, that just goes off to infinity. This, and we've done this one before actually. This integral diverges. This is divergent. which I hear is a pretty good movie, and I believe they even made a book out of the movie. Yes, I said that wrong on purpose. It's supposed to be funny. Laugh. God, you guys are so uptight. All right, so this series is greater than a divergent integral. Therefore, this series must also diverges by the integral test. And that's what you can say. And that would be your reasoning. Okay, now you're not drawing the picture and you're doing all that. You're doing the integral, because whatever the integral does, the series will do. As long as the series itself has to be decreased. Remember, it has to pass like the gateway test and all that. In fact, you know what? Let me show you that, because I don't think I got to really show you this in class. Let me just pull this out of the book real quick so you can have it in your notes if you didn't already see it. Let me see if I can get this to look good here. Here, this is a real fancy definition here for you. Okay, and it's everything we've said. Let me focus it for you. Let's see, where is it? Hang on just one second. Okay, much gooder. All right, so look, you've got a continuous, positive, and decreasing function. So those are all the things that we've basically been dealing with. The only thing about the decreasing is it's when we do our gateway test, we're talking about it's decreasing to 0. So sometimes you have to actually show that. Usually they don't try to trick you with that, but you should at least keep that in mind. Don't forget about our gateway test, our test for divergence. So assuming everything's in place, then you're basically turning your a sub n into a function, which is what we did, and it's basically telling you that the series is convergent if and only if the improper integral is convergent. So basically exactly what we said. If the integral is convergent, then the series will be convergent, or if the integral is divergent, then the series will be divergent. Okay, so that's just the fancier definition for the integral test. But I guess you should probably see that. I think we explained it, but some of you I know like to have the definitions, so there they are. Okay, so that's actually really it for the integral test itself. It's basically using an improper integral technique to determine convergence or divergence for a series. Okay, I'm going to stop the video here. I'm going to go ahead and do an example in the next video, and then I'll show you the p-series. Okay, let me know if you have any questions. I'll see you later.